Hello everyone. Welcome to session 2 of Epoch 1 or GANs all you need. So today we'll be looking at two very interesting application of GANs. I'm Niveth. I'm an analytics club coordinator. I'll be handling the first GAN and following me Priyanka will be handling the second GAN. So before we get started with today's GANs, we will look at a short recap of what we did yesterday just to refresh your memory. So yesterday we just got into GANs. So what are GANs? So GANs, unlike other models that might try to classify your images, like they could classify a dog or a cat, they could classify messages into spam or not spam. But GANs, they try to learn the actual distribution of the data. So what is the great thing about learning the distribution itself is that you can generate your own new fake data. So that's why GANs are so powerful. So the two major parts of GANs are the generator and the discriminator network. So generator, what it does, it takes in some random noise and it gives you a fake data as its output. The discriminator, on the other hand, it tries to classify the data that you give it, whether it is real or is it fake. So that's the role of the discriminator. So coming to how you train GANs. So the way you train GANs is called alternate training. So when you train the discriminator, you give it data from both the generator and the real images from your data set, and you train it to classify them as real and fake. But and one thing is, when you train the discriminator, you don't train the generator. So all the parameters of the generator are kept constant. Then after you train your discriminator for a couple of epochs, you train your generator. When you train the generator, you keep your discriminator constant and you train your generator to produce better fake images and fake data. So how do you tell the generator that it's doing well or if it's doing bad? Is by using a loss function. So this is the loss function that we use in GANs, and it's called a zero-sum game. So in this equation, as it was explained yesterday, the first term in this equation, what it represents is how good has the discriminator classified the real images as real images. And the second term tells you how good has the discriminator classified the fake images as fake. So for the discriminator, since its role is to classify images, you want this to be maximized. You want that it classifies its real images as real and fake images as fake. But for the generator, you want to fool the discriminator, right? So you want the discriminator to be not be able to tell the difference between a real and a fake image. So you want to minimize this loss function. So that's how you train your generator. So that's a quick recap of what we did yesterday. So if you have any doubts, you can ask it now about what we did yesterday. Okay, so we'll get started with the first GAN for today. So today we'll be looking at SR GANs, which stands for Super Resolution Generative Adversarial Networks. So what is super resolution? So super resolution is basically you take some image that's of lower resolution and you try to increase its resolution. You Yes. So you basically upscale a lower resolution image into a higher resolution image. So obviously why you do this is because higher resolution images offer more detail and they just look better, right? So to give you an example, so this is what we are trying to do. So on the left is an image that's not of very good resolution. You can see it's quite blurry. So you basically want to convert it into something that looks like on the right. That's very clear, right? Another example. So today we'll be looking at a GAN-based method for performing super resolution. So SR GANs have been known to perform up to 4 times upscaling. So if you have an image, you can increase its resolution by up to 4 times. So that's quite the improvement. So before we get into the architecture and the working of SR-GANs, we will look at some concepts that we need to understand SR-GANs better. So first, so yesterday we were doing convolutional neural networks. So what actually do you do in a convolution, right? So basically you perform something called as the kernel operation or a convolutional operation. How do you do a convolution operation is you take a matrix of weights and you take a small window in the image that you have that is of the same size as your matrix, and you perform element-wise multiplication. So that's what a kernel operation or a convolution is. So the size of this kernel is called the kernel size. So one option that you have while performing convolution is you could possibly skip over some pixels between successive operations. So in the left side of the image, you can see that it has taken very adjacent squares, right? So that is called a stride 1 convolution. On the right, you can see that it has skipped over one column of pixels. So that is called a stride 2 convolution. So, okay. So this is a small video of how you do a kernel operation. So you can see that you take some matrix of weights and then you just move it over your image and perform a convolution operation over each small part of the image. So what you do by this is basically capture the features in those small areas. So that's why you do convolutional operations. So there is one problem with the convolutional operations that you do. The thing is, suppose you had a 3 into 3 kernel, as you can see here. So if you had an image, now the corner pixel will be covered only once by this convolution, but the edge pixel will be covered thrice. But a pixel in the middle of the image will be covered 9 times. So what happens is there is some kind of loss of information from the edges and the corners, and there's kind of a bias towards the middle of the image. So if there was some important feature at the edges or the corners of the image, that it is very likely that it will be lost, but you obviously don't want this to be to happen, right? So what you do is you do something called padding. Padding is basically you add an extra layer of pixels around your image. Now you can see that I've added a layer of just zeros around the image that I have. So now you can see that the corner pixel in our original image is now in the middle of our new image. So all the pixels of our image will be covered equally. So there is no loss of information from the edges or the corners. So that is why you do padding. Okay, so do you guys have any doubts on kernel stride and padding? All right. So next we'll be looking at a concept called batch normalization. So yesterday we were talking about batch propagation and gradient descent. So when you do gradient descent for a particular parameter, right, you basically assume that all the parameters of the layers prior to that neuron that you're trying to update is constant. You basically find the derivative of the loss function with respect to that parameter alone. But when you have deep models and you have a lot of parameters, as your input passes through the model, right, it is very easy for the weights and the output from the neurons to be greatly varying in magnitude. So when this happens, your model becomes very unstable and the backpropagation is not really good. Your training is unstable and your model is kind of chasing a moving target, because every time the weights of a previous layers change, your optimum is something else, right? So how do you reduce this? So this phenomenon is called as internal covariate shift. So how you reduce this is by doing something called batch normalization. So what you do is you normalize the outputs from each neuron after every layer of neurons. So normalization, as you might know, you just subtract the mean and divide it by the standard deviation. So even when you have when your input data is largely varying in magnitude, when you normalize it, they all come together, they come closer. So that's what you need. You don't want them to be greatly varying in magnitude because then your back propagation is not stable. So when you perform batch normalization, it is observed that your training is much faster. So your model will converge quickly. And also this provides a regularization effect. So if you don't understand it, it's fine. It's not really necessary. Do you guys have any doubts in batch normalization? Yeah. Sorry. Previous slide. Yeah, you had a doubt? I can't hear. So why it acts as a regularization effect is actually some other parameters that come into batch normalization that actually add noise into the data. So when you add noise, it is harder for your model to overfit to the data. So it provides a regularization effect. Any other doubts? So yesterday we were looking at activation functions, right? So this is one type of activation function called as a ReLU, rectified linear unit. So the math of ReLU is pretty simple. When the input is positive, it just lets it through as it is. When it's negative, it doesn't lets it through. It's zero. So why do we use ReLU is because the slope of it is 1. If you use some other activation function like sigmoid, uh, which has a gradient of maximum of 1 by 4. So when you have very deep models, in very quickly the gradient of it will fall. So that's a problem. We'll be looking at this problem a bit more deep in a couple of slides. So one upgrade to rectified linear unit is leaky ReLU and parametric ReLU, which is abbreviated as PReLU. So in leaky ReLU, instead of completely truncating the negative part of your output, you let a small portion of it through. So you basically multiply it by a very small number. Like in this image, it's multiplied by 0.01. But based on your model, you would choose some other parameter and you would multiply it and allow this small part through. Another upgrade is PReLU. So in PReLU, what you do is you allowed the slope of this negative region to become a parameter of your model. So as your model trains, it would choose the value of this slope such that it works best for your model and the task that you're trying to do. So now I've got a question for you guys. So why do you think we might use leaky or parametric ReLU over normal ReLU? Okay, let me give you guys a small hint. So think about the slope in the negative region and what would happen to a neuron if it outputted a negative value. You can just give any thoughts that you might have. It doesn't need to be correct, just anything. So yeah, so what he said is if the slope is 0, basically the gradient of the loss function with respect to it would become 0. So what that means is so this is called as the dead neuron problem. So since the slope of ReLU in the negative side is 0, if a neuron outputs a negative output, it never gets trained. This parameter is always constant. So if by any chance, if a lot of neurons in your model output a negative value, it would lead to a large part of your model practically doing nothing. So this leads to an inefficiency, right? Your model does not perform to its best extent. So that's why you perform leaky ReLU or parametric ReLU so that you can let a small amount of your negative outputs through. So this will improve the gradient. So even if the output was negative, it would still get trained. It might get trained slower, but it will still get trained. So do you guys have any doubts in ReLU, parametric ReLU? All right. So now we'll be looking at the vanishing gradient problem that I was talking about before. So sorry that the image is horizontal. I couldn't put it straight. It was becoming too small. So this model that I have put up there has 34 convolutional layers. All right. So when you have this many layers, towards the deeper parts of your model, it is very likely that the gradient becomes extremely small. So when it does become extremely small, your back propagation becomes very inefficient, because when multiplied with the learning rate, the actual training that you will do to each parameter is very less. So your model might converge, but it might take too much time, and it's not practical to be in such a situation. So how you resolve this is by using something called skip connections. So in skip connections, what you do is you basically add your input directly to your output. So you can see here, there is some input X, you perform some operations on it, it gives you some f of X, and then you add your input X directly to your output. So you can see that if you now differentiate this, right, this additional factor of X, it will give you a gradient that is more closer to 1. So your gradient wouldn't become too small that quickly. So also what this means, since you're directly adding your input to your output, it means that your deeper layers will perform at least as good as your more shallower layers, right? Because you're adding your input X directly to your output. So do you guys have any doubts in skip connections? Why we use them? I guess we'll move on. So now we'll get into the architecture of the GAN that we want to be that be seeing today. So today we are seeing SR GANs. So like any other GAN, it has two major parts: the generator and the discriminator. Now, unlike the GAN that we saw yesterday, which only uses the zero sum game loss function, we'll be having a special loss function today, because we want to do a specialized task. We want to improve the resolution of the image. So we'll be using a loss function that will help us in this process. So first we'll look at the architecture of the generator, and then we'll move on to the discriminator. So the generator architecture can be split into two major parts. One is the residual blocks. So you can see the residual blocks at the beginning of the architecture. And after that, you have something called as a sub-pixel convolution. So the sub-pixel convolutions are the actual layers that increase the resolution of your image. So what you do with your residual blocks is basically capture the features of your image, and then using your sub-pixel convolutions, you upscale them. So in the residual blocks, the architecture is pretty simple. So you have a convolutional layer, and you have batch normalization layers, and then you have skip connections. So can you guys guess what this K3N64S1 means? Like, we're talking about something at the beginning of the lecture today. Yeah. So K3 basically means kernel size 3. Can N60, yeah, and S1 means stride 1. Can anyone guess what N64 is? Sorry. I heard depth of. Yeah, okay, so that's kind of right. So what N64 means is the number of output features that you want your convolutional layer to have. So your input image would be having 3 channels. Now, after this convolution, you basically want your output to have 64 channels. So can anyone tell me why input has 3 channels? Yeah, so because you're trying to put in a RGB image, so it'll have 3 channels: red, green, and blue. Now, after this convolution, you want the image to have 64 convolutional layers. Now, the number of residual blocks that you use is something that you will be deciding. So all these parameters that you will be deciding before you train the model are called hyperparameters. So the number of residual blocks that you have is called is B. We'll be calling it B, and that is a hyperparameter. So we'll be looking at subpixel convolutions now. So you can basically think of subpixel convolutions as a two-step process. So first, what you do is you increase the number of features in your image to a particular factor. Now, suppose you want to increase your image size by a factor of R, then you will increase the number of channels in your image by R square. So you can think of this as taking each channel in your input image and dividing it into R different channels. So that's what step one is. So this is what happens. You take one channel and divide it into R square number of channels. So in the second step, what you do is you take these R square channels and you rearrange the pixels in order to increase the resolution. So you can see here, we have R square C number of channels, right? So we rearrange the pixels so that we have R times the initial height and R times the initial width. So more commonly, these layers are called as pixel shuffling layers. So you can see what happens here. So you have these channels here, and you can see that in each of the pixels in the higher resolution image, you have basically taken like an entire row of one of these channels and you've put them there. So you can see red, orange, yellow, green, and so on, right? I hope that's visible. Did you guys get what I'm trying to say? Like here, you take this red pixel and so so our initial convolutional, so our input had 5 into 5 pixel size, our image. So you can see there is 5 into 5 pixel size. Now you can see that each of these 5, each pixel in our initial image has been scaled up R times in height and width. So to get those R square pixels, you take this red pixel, put it in the first place of each of the pixels. Then you take these orange pixels, put it as the second. Then you take the yellow, put it as the third. So are you able to see that in the image? Yeah. Do you guys have any doubts in subpixel convolutions? All right. Yeah. Color map meaning I didn't understand you. Yeah. So in between, it might be like less than like uh, not really able to understand your doubt. So the pixels have values ranging from 0 to 255 is what you're saying. Yeah. Yeah, that's why we do training, right? So when you train, the weights and the parameters get trained such that your final image will resemble your original image. So here you can see what happens in a subpixel convolution. So you initially increase the size, and then you can see that each row of one of these channels is becoming a separate pixel in the new image. So I've got a quick question for you guys. So what do you think is the output size of the generator network given that the convolutional layers use same padding and the input image has size 3 into 96 into 96? So I think I forgot to mention about same padding. So what does same padding mean is that you add padding layers sufficiently enough so that your input and output have same dimensions. Anyone, any thoughts? Okay, so guess I'll answer it. So you can see that all the convolutional layers use same padding. So like I said, your input image and the output image would not differ in its dimensions. So if your input image has size 96 cross 96, so all after all these convolutional layers, you would still have a 96 by 96 image. The only places where your size would increase is in the pixel shuffling layers, where your size would increase by a factor of 2. And you have two such pixel shuffling layers. So basically your size would be 4 times 96 times 4 times 96. That's that's 384 cross 384. So do you guys have any doubts in the generator architecture? Yeah. Uh, yeah, basically what you're, so you have some image that's of some size and you want to increase it by a factor of r. So what you do is you split each channel into r different channels. Just a second. So you split each channel into r different channels, and that's why you get this r square channels there. So this is what happens. Now you reshuffle these pixels and you make them, you reshuffle these pixels so that your height and width of the image increases by r times each. And this is where the training part comes in. So you'll train the model such that this net image that you get has more texture and more quality than your initial image. So we'll move on to the discriminator architecture. So the discriminator has a very simple classification type architecture. So you basically have a number of uh, convolutional layers where you gradually decrease the size of your output and you increase the number of channels. So what you're trying to do is capture more features in the convolutional layers. So that's the first part of your discriminator. So at the end of the discriminator, you will be having output size that will have 512 channels, as you can see. So the last convolutional has 512 channels. And then yesterday we talked about a concept called flattening. So what we mean by flattening is after the convolution, you have an image that's of particular size, but it's a 2D vector, right? You basically flatten that vector and make it into a 1D vector. So that's what we mean by flattening. So this flattened output is passed through some fully connected layers, And at the end of the fully connected layers is a sigmoid. So can anyone tell me what is the output range of a sigmoid? Yeah, so the output range of a sigmoid is from 0 to 100. So what the sigmoid outputs, so that's my question for you guys. So what does the output of the discriminator signify? Yeah, so basically the output is the probability that the image is real and not something that we blew up the size of. So that's what the discriminator's probability represents. So any doubts with the discriminator architecture? Yeah. Yeah. No, no. So what we need the super resolved image to have like a similar quality of a actual high resolution image. So what the discriminator classifies is not just based on the size of the image. It'll actually look at whether the real image and the super resolved image has similar quality and perceptual attributes, right? So whether all the textures are there, whether it is as sharp as a real image. So those kind of features are also looked at by the discriminator. Anyone else? So as usual, as in again, we have the adversarial min-max problem. So min-max is just another word for the zero-sum game. So here you have the min-max. So the first term represents whether the discriminator classified the real images as a real image. And the second term signifies whether the discriminator classified fake images as fake. So can anyone take a guess at what HR and LR mean? Just a blind guess. Yeah, so HR stands for higher resolution, LR stands for the lower resolution. So D represents the discriminator, G represents the generator. So what D of IHR means is the probability that the discriminator thinks that that particular image is real. And what G of ILR is the generator's output of the lower resolution image. And D of that is the probability that the discriminator thinks that that image is fake, real, sorry. So that's what the problem is. So for the discriminator, which is trying to classify images correctly, you need to maximize this because the discriminator output of 1 means that the image is real and the discriminator output of 0 means that the image is fake. So if all the real images got a value of 1, then the first term basically becomes 0. Or if they got value less than 1, their value would be negative. And if all the fake images got a value of 0, then the second term also becomes 1. So you want to maximize this value for a good discriminator. As for the generator, you want it to be able to fool the discriminator. So it wants a value of 1 for all of the generated inputs as well, generated images as well. So when the generated image gets a value of 1, the second term would go towards minus infinity, right? Because log of a value less than 1 is minus infinity. I mean, it goes towards minus infinity. So for a good generator, you want to reduce this value. So now we come to the part of defining a separate loss function for our task. So how do we compare two images? So if I gave you these two images and asked you something about which one is more clear, you would obviously say the right one. But how do we quantify this? So there are usually two metrics that are used. So the first metric is the mean squared error. I think that's pretty obvious. So basically, you find the difference between two pixels the corresponding pixels in two images and find their average. The peak signal to noise ratio is something more involved that we do not know much about it. We just need to know that for a good image, you want a lower peak signal to noise ratio. Now, in the formula, you divide it by the mean signal noise ratio, right? So if you reduce your MSE, you will basically increase your peak signal to noise ratio. Yeah. So how good are these traditional metrics for our task? So when you have a particular pixel that you want to increase the resolution of, so when you have that blue pixel, so you have a number of possible solutions for that pixel that are represented by these red pixels. So when your network simply tries to reduce the MSE, the best way is to go towards the average of these pixels, right? Because then you would bring down the net mean squared error. So you would get something that looks like the blue pixel, but you would actually want some of those textures and the features that you find in a high resolution image. So that's why we use a GAN. So basically, when you use your normal metrics like MSC, you lose all your visually perceptible attributes like textures and sharpness. So we introduce another very interesting loss function called the perceptual loss. So the way we write this down formally is given by this equation. It's not really important. I'll explain it. So content loss is the part that we are concerned of. So content loss is what and adversarial loss just deals with fooling the discriminator that we saw about it earlier. So the way we approach content loss by using a completely different neural network called VGG19. So I've put the architecture for VGG here. So the VGG19 architecture is the final column in the picture. So what we do is we take our higher resolved image, we take our actual input image, we pass both of these through a already trained VGG network. And now we take their feature maps from a certain layer for both of them and calculate the mean squared error of these two feature maps. So can you guys guess how does this actually work? So why does this work? This gives really good results. So why do you think it works? Any thoughts? You can think about what CNNs actually try to capture from image and what we want as well. Anyone? All right. So the thing is, what does a CNN capture in an image? So the CNN basically tries to capture the features of an image. So if you took an example of identifying a face with a CNN, for example, so your layers might initially identify features like edges, curves, small shapes, and stuff like that. Your later layers might begin to identify features like small parts of your face, like a nose or an eye. And your final layers of your convolutional network would be able to identify complete faces. So that's how a convolutional neural network works. You begin by identifying small features in your image, and you slowly increase your ability to identify entire faces. So that's how a convolutional neural network works. So when you have two images that are similar in features themselves, obviously the feature maps of their VGG network would also be very similar, right? So by reducing the distance between their feature maps, you can say that you are also bringing their features before the VGG, the input features to be also be very similar. Does that make sense? Yes. So we will just quickly look at this equation. So what does phi ij mean is you take the jth convolutional layer before the ith max pooling. So that's just a small. So if you look at this, so in the actual implementation of SR GANs, what you take is 5 4. You put I equal to 5 and j equal to 4. So you take the fourth convolutional layer before the fifth max pooling layer. So can you guys tell me which layer that is? The fourth convolution before the fifth max pooling layer. Yeah. Yeah. So no, the fourth convolution before the fifth max pooling. So the last max pool is the fifth max pooling. So four before that is that one. So one thing is, as I told you, the as your convolutional layers go deeper, they'll be able to identify much larger features in your image. So I think you can say that if you take a convolutional layer that is deeper, you would get better results, right? Because you're able to identify much larger features. So in practice, you actually usually take the last convolutional layer there. So in practice, you usually take the last convolutional layer, and that seems to give the best results. So VGG22 is basically you take the second convolution before the second max pool. So I think you can identify which convolutional layer we're talking about. That would be the third convolution from the top. The second convolution before the second max pool. And 5-4, we just saw what it is. So perhaps you can see that 5-4, like it gives more texture and more detail than 2-2, right? Can you guys see it? Yeah, so it's just for example. So basically we use deeper convolutional layers and that would give you a better result. So, and then we come to adversarial loss. So you want the generator to fool the discriminator. So this is the adversarial loss that actually concerns the generator. Now in our original, yes. Uh, Input images as it is. I mean the yeah. Convolutional layer. Yeah. No, like perhaps I should. mm, So, okay, so how this actually involves a little of how we actually train the generator. So what you do for, how do you, so how do you train the generator? So you need you super resolve some image, you need something to compare it to. So how we actually get the input to the generator is we take the original high resolution image. So the right one over there, and we perform some random downsampling features, some random things, and we bring it down to a lower resolution, and that is our actual input to the generator. So I'll be going a little more into this at the end. So what we do is, to our VGG90 network, we'll give the super resolved image from our generator network and the original high resolution image. So that's what I mean. So if these two are similar, their feature maps will also be similar. So that's what I meant. Yeah. Does anyone else have any doubts? So, so this is the adversarial loss. So here I have written it slightly differently from our original adversarial loss. So this was explained yesterday as well. So can any of you tell me why we might use this one instead of writing it as log 1 minus DGILR? It was explained yesterday as well. Any thoughts? Why we might use this instead of using log 1 minus the discriminator output? Not exactly. Can you think about like the gradients of this function and that function? That might get you the answer. So the thing is, when you take the gradient of this function, you will get much larger gradients than the gradients of the original log 1 minus d function. So why you want that is the training of the discriminator is pretty easy. It's just a normal classification model. So if your discriminator gets really, really good at classifying real and fake images, your generator will find it extremely hard to train because whatever it outputs, it will say it's wrong. So your generator doesn't know in which direction to go. So that's why you take this loss function because it gives a higher gradient and it will train your generator at a faster pace. Does it make sense? Any doubts? So now we are coming to training the model. So when we are training the discriminator, we simply care only about the adversarial zero sum game loss function. So we'll just try to maximize this. So we, like other GANs, how we train the GAN network is by using alternate training. So we alternatively train the discriminator for a particular number of epochs, and then we train the generator for a particular number of epochs. So when we train them, as I said before, the input to the generator is a low resolution image. It's not random noise as we were talking about it tomorrow, because that is the task that we are trying to do, right? We are trying to take some low resolution image and get a higher resolution image. So we want our GAN to also function that way. So the way we get this low resolution image is we take a higher resolution image, apply some kind of downsampling, we do some operations on it and reduce its resolution, and we train the and we input it to the generator, and we train the discriminator to reduce the adversarial loss. And the generator, we try to reduce the perceptual loss that we saw. So the perceptual loss is what is represented by LSR. So that's the perceptual loss. Do you guys have any doubts in training? Yeah, all right. So we'll just look at a quick example of how SR-GAN works with respect to other models that are used for the same thing. So we need not know about the other models much, but you can see that SR GANs and the original image looks almost similar. So before SR GANs, the model that was primarily used was called SR, very plain, and it is really smooth. You don't get all the texture and all the sharpness that you get from an SR GAN. So, and you can look at another, it is not really visible in this image, but yeah, so SR GAN is just now the benchmark for super resolution and such tasks. So do you guys have any doubts about what we just discussed? Anything at all? Yeah, so basically after you train your GAN, you don't need the discriminator anymore. because the discriminator is only to aid the generator and telling it whether you're doing well or you're doing bad. That's what the discriminator does. So once you're done with training, you can basically do off with the discriminator and can just use the generator and give it an image and it will produce a super resolved image. Anything else, guys? Yeah, I hope that was interesting. So yeah, so that's the end of part one. So next we'll take a short 5-minute break, and after that Priyanka will be continuing with an other type of GAN.
Guys, we'll be starting off in a minute so you can settle down. And Nivet is still solving the doubt. Nivet. Okay, hi guys, I'm Priyanka and I'll be taking the session on cycle GANs. I would like to start with the motivation behind this model. So, what if we had to do a season transfer, like suppose transforming this image of a summerscape to a winterscape, or of converting a horse to a zebra, which is essentially object transfiguration, or making this Monet painting into a photograph as if the camera was present at that moment, taking the same exact scene. So for this, we have what is called as a cycle GAN, a cycle generative adversarial network. So it uses unpaired image to image translation to capture the special characteristics, and then using these learned characteristics to like make new images. So first we'll see what unpaired and paired data sets are. The first column you can see is paired data sets, where every element in the first set is mapped to the second set, like it's a one-to-one mapping. So for this example, it's like a single line shoe is mapped to a solid shoe. But in an unpaired data set, you have multiple sets with no relation among themselves. So it's not necessary that any element in a set has a corresponding element in the other set. So how CycleGAN uses this is it finds out the similar characteristics in a single set and the differences in characteristics between the sets, and then learns from them. It's better to use unpaired data sets in such a problem because we don't have enough data in like paired form. Suppose like we may not have a Monet painting for every photograph that we provide as an input. So therefore unpaired data sets help. And also for some problems we are not even like don't have defined outputs that we expect. So therefore CycleGAN is a better image to image translation model than the other models that use paired data sets. So like in a generator, like any GAN, this has a pair of generator and discriminator. The generator starts off with noise and creates a zebra from a horse. And then we saw from the previous session how it does that. So I would like to ask you a question. Like we have a given image of a horse and there are two output images. Which of the following zebra images do you think that the generator will generate? The first one? Okay, so here the generator generates both the images because the generator is given the task to create a zebra. Now, if it starts with noise, it knows only one goal, make a zebra. And essentially both the images are a zebra. So even the discriminator doesn't say that it's wrong. The discriminator says that you've done a good job. So the generator creates both these images and both these images are considered as valid. But what we want a zebra that corresponds to the image of the horse that we've provided. Like we want the entire background to remain the same, the shape of the horse to remain the same, except that the horse's like color changes and it gets stripes. So this is what we call a mode collapse, when we provide multiple inputs but all of them like give only a single output, and in this case optimization is difficult. So I would like you to divide yourself in groups of like 4 5 and think over a solution for this. So I'll give you like 5 10 minutes. And how do you think we can solve this problem from what we've learned, like generators and discriminators? How do you think we can solve the problem of getting multiple outputs for a single input and vice versa? Like, have you come up with a solution or like a crude model? Yeah. Okay, but there's a very like simple, straightforward solution that this model uses. Like, but but in this case, your generator wants to like knows only that it has to create a zebra. It doesn't know that it the zebra has to be like the first horse. Yeah, you're going like closer, but we want an architecture that says that like step A, B, C, like that. Using noise is a plus point because using noise makes like ensures that we get a wide range of images. If we used a blurred image, we will get the same type of images over and over again. It's just better to train with noise, like you can optimize it better. Sorry, I didn't get it. But how will like the numbers do this? Like everything's going to be converted into numbers when we use the CNNs in the model architecture. So once we overlap them, essentially they'll become noise again, right? So should I move on to the answer or do you want to think more? Okay, let's move on to the answer. It's a very straightforward method, like which is what makes this model neat. Is instead of using just one pair of generators and discriminators, we use two pairs. One that goes from a zebra to a horse, and the second that goes from a horse to a zebra. So in this case, what we do is that the first generator, let's call it a function g, goes from x to y, and the second generator, a function f, goes from y to x. And now what we have only one task to see that the reconstructed image, what if, like, let's call it x dash, if x dash and x are equivalent, and if they are equal, then we can say that the image between, like, the horse is also correct, in the sense that what it's the output that we wanted. So here we have to only check if the horse, the discriminator will work and see if the horse is correct, and also check if the zebra is correct. And also what we introduce next is we will compare x dash and x and see if they're equal. So I would like scan this QR code. There's a question, and I would like to have a discussion on this question. What do you think is the answer to the question? Would anyone like to volunteer to like answer? Anything? What do you think the answer to the question is? Which option do you think is the best, like, loss function? Option three. Option three is not the best option. There is an option better than that. I kind of gave away the answer, but yeah. Option three essentially like sums up the entire like motivation behind the loss functions. But like, okay, I will move on to the answer. The option four, like, is a better option because here it just represents that the discriminator, there are two losses. One that checks the loss for like only the set x, like horses, and the another that checks for y, and that is the zebras. And the second one is the loss where we check between x dash and x to see if the like input image and the reconstructed image is the same, which is like what is different here. Moving on to the model architecture, first firstly, the generator, it has an encoder, transformer, and a decoder. The first three blocks that you see is an encoder, which has a convolution layer, instance normalization, and ReLU. The convolution layer here like captures the surface layer features such as edges and lines, and the instance normalization is done to basically bring all the data to a level ground so that it's easier to make sense out of the data. And the ReLU is the rectified linear unit which we use for as an activation function. And this transformer, which are the orange blocks here, are made of residual blocks which, like Nivet said, use skip connections, so that usually when we have a deep neural network, the network forgets the information that it learned previously in the shallow layers. So we use skip connections so that we provide the output of previous layers as input in the further layers. Like suppose if we have 5 layers, 1, 2, 3, 4, 5, we provide the output of the first layer to the fifth layer. So the fifth layer will have input that comes from the output of fourth layer and the first layer. So this ensures that we don't forget the information or miss out on it. And the next part is the decoder, where we have a transpose convolution layer, instance normalization, ReLU, and convolution layer. The difference here is the transpose convolution, it is kind of doing the same job as a convolution layer. Only difference is in a convolution layer, we kind of compress the image and like reduce the dimensions of the image, but a transpose convolution increases the dimensions of an image. Talking about the architecture of a discriminator, it is kind of different from a normal GAN in the sense that it uses patch GANs. In a normal GAN, the discriminator gives the value real or fake for an entire image. But here, we, the image is divided into n by n boxes, and the discriminator here gives a value real or fake for every n by n box that we divide it into. And then all these like true or false ones and zeros are averaged out, and one single value is given out. In this also we use convolution, like it's the same structure, only difference is that here as an activation function we use leaky ReLU and sigmoid function. So this was the forward pass, and then a loss function, the like basic loss function, the adversarial loss function of a GAN is where the discriminator sees if it's real or fake. And in the loss function, the log dy term that we see is the term that says if the image is real, and the log of 1 minus dy g of x tells if the image is fake. So E is the expectation, where we basically take the average of all these values and get the final loss. The next loss function is unique to the cycle GAN, which is the cycle consistency loss function, where, like I said, we compare the image X and the reconstructed image X dash to see if they are equivalent. Here, G of X gives us Y, and F of G of X gives us X dash, essentially, which is a reconstructed image. So X dash minus X is the difference between like the input and the reconstructed image. So usually when we want such differences, we use mean square error, which is X dash square minus X square. But in this case, when we use mean square error, the like it softens the image, so we lose a lot of clarity. Instead, here we use just the difference, and E is again the expectation, so we average out all the individual losses to get the final loss. And the backward prop, like back prop of this GAN is also the same as every other GAN. Depending on what a discriminator gives as an output, we train the generator and the discriminator. The discriminator, if it gives says that the image is fake, then it has caught the generator. So the generator trains while the discriminator remains idle. And if the discriminator says that the image is real, the generator has done a good job, and the discriminator needs to train itself to like guess the image better. So in this part, the generator remains idle and the discriminator trains. So I trained the cycle GAN, and for 15 epochs, that in itself took an hour. So this is what I got as an output. You can see that it's very crude and it requires much more training, up to like 5,000 epochs. So this is how it will be if we train it to like 100 epochs versus 5,000 epochs. As we train like for more epochs, the cycle GAN gets better. So you can see in the first image for 100 epochs, the image is very blurry and crude. And for 5,000 epochs, it's almost like close to what we expect in the output. And then limitations, like even though cycle GAN is very versatile, it has its limitations in the sense, if I tell it to convert a cat to a dog, this is the hideous image that it will provide. So it cannot do shape transfer. It can only like keep the shapes the same and change the style or texture of the image. And in the second image, if we provide this image, it's what we call inductive bias. So the generator is trained on a data set of only horses. So it can recognize horses. But if we provide a human in it, it cannot recognize a human and considers the human as a horse too. So in this case, it converts, like, gives the human stripes and makes it into a zebra too. So another question, scan this QR code. So what do you think is the answer? Yes, composition and, yeah. So why not the other two? Or why this? Both? Yeah. Okay. So yeah, a patch GAN enhances composition, texture, and style. The texture and style is like what a convolution does. It takes information about it, and then this is essentially what a cycle GAN is doing. It's doing transformation in the sense of textures and also composition. You can see the patch GAN like n by n square as a kernel in a convolution. So if the n by n, like value of n is large enough, we can get enough information about composition. Like common patch GANs are like 16 by 16 and 70 by 70. So in 16 by 16, we cannot say that that a patch GAN enhances the composition. But for cycle GANs, we use patch GANs of 70 by 70. So yeah, it does retain information about composition. About resolution, we get the like understanding about resolutions through the loss function where we calculate the difference between x and x dash. So the loss function essentially says, like, it compares x dash with x and then says if x dash has a poorer resolution than x, then that way the generator will train itself to get better at resolution, not through the patch GANs. And also for colors, colors are just like data in the decoder, so not in the discriminator, it's part of the generator. And do you have any questions, any doubts? It's usually mostly used in photo enhancement, like the, you know, bokeh mode, right, in the phones, like portrait modes where the face remains in picture and the background blurs out. That's one of the most common, where it changes the texture of the background. Any other doubts, questions? Okay, then that, yes. No, PathGAN is a part of discriminator. The discriminator only checks if the image is real or fake, or like checks if the characteristics are correct. So it's not going to change the color for it. Okay, so that's it for this session, guys. Thank you.